Hello class, in this video we are going to go through chapter 6, section 1, the standard normal distribution. So we should know by now that the normal distribution is a bell-shaped curve. It's symmetrical around the mean value as well. So 50% of all the values will be to the left of the mean and 50% will be to the right of the mean. The total area underneath the curve is 1 or 100%. The areas can be thought of as probabilities. So, for example, if you take the area of the curve to the left of the mean, that would be 0.5 or 50%. Areas can be written as percentages. Areas cannot be negative. You know that you can't have a negative probability. And if the data is continuous, continuous things like height or a value that isn't discrete, the probability can be called a density curve. Okay, so normal distribution, if a continuous random variable has a distribution with a graph that is symmetric and bell-shaped, we say that it has a normal distribution. And this is a complex, convoluted formula, which I will never ask you to do manually, but that's just for an FYI. I don't know why it does that. So another type of distribution is a uniform distribution. We know that a uniform distribution, all the values could have or will have the same probability, so you're just as likely to get a 1 as you are a 2 or a 3 or a 4 or however many x values you have. So the area underneath a continuous probability distribution is equal to 1, so the area underneath this would be equal to 1. Number 2, for the properties of a uniform distribution, probabilities can be found by identifying the corresponding areas in the graph using the basic area of a rectangle formula. So area equals height times width. Also note that the probability over here, this p of x, would be 1 over the highest value of x. What I mean by that is, so say your x values is number of minutes you have to wait in line at a store, and it's completely uniformly distributed. So your p of x value would be 0.2. So there's a 0.2 probability you'll get 0, 1, 2, 3, 4, 5. All those values would be the same probability of 0.2. And 3, a continuous random variable has a uniform distribution if its values are spread evenly over the range of possibilities, thus getting the rectangular shape. So let's look at an example. Waiting time for an airport security. During certain time periods at JFK Airport, passengers arriving at the security checkpoint have waiting times that are uniformly distributed between 0 minutes and 5 minutes. So we see that since it's 1 over 5 gives us 0.2, that's where this height comes along the y-axis. And since it's continuous, remember, a minute could be, or a time could take on any value between the 0 and 5. It could be, if it's 1 minute, maybe it's 0.01 or 0.001. That's why it's continuous, since there's an infinite number of times that occur between 0 and 5. And all values are just as equally likely to occur. Kind of already went over that. So the probability, again, is 0.2. You already went over that. Okay, we're ahead of the game. So given the uniform distribution illustrated in the figure, find the probability that a randomly selected passenger has a wait time of at least 2 minutes. So when you hear at least, immediately your mind should be 2 or more. So that could be 2 minutes, 3 minutes, 4 minutes, 5 minutes, 2.2 minutes, any value from this point, take a straight line, go up, at least would be this point up, that vertical line, and all values to the right of that. If this problem X at most 2 minutes, it would be that vertical line at your 2 minutes, and then you'd be looking for the area to the left of that vertical line. But this problem we are looking for at least 2 minutes. So to find the solution, we want to know what the shaded area is that represents the waiting time of at least 2 minutes. Well, this is a rectangle, so it's pretty easy to find the area under the curve. So we have just your standard area for a rectangle. So we have a 0.2 as our height. Our width would be 5 minus 2 is 3. So we have a 60% probability that the wait time is at least 2 minutes. So what if the distribution is normal, not uniform? It's the same. To find the probabilities, it would be the same logic that you're finding the area under the curve, but how are you going to find the area under a curve like that? It's not a linear line. It's much more difficult to just do that just from basic algebraic expressions. So for this, we will have to find what's called a standard normal distribution, and that's kind of the premise for this section. So a standard normal distribution is a normal distribution with the parameters of mu, which is the mean, of 0, and standard deviation equals 1. And the area under the density curve is equal to 1. So basically what you're doing is we're used to seeing normal distributions where our mean is just the mean of whatever value that we happen to be analyzing, and the standard deviation is calculated from that. Now this standard normal distribution is kind of like, if you guys remember, maybe unit circles back in trigonometry, which is just a way to have a standard unit measurement. So it's a way of taking any type of normal distribution and being able to apply a single type of procedure to be able to find data from that, similar to how you use the unit circle to figure out your angles and your radians for any length hypotenuse in algebra class. So let's take that, and let's now look at, we're going to go back to the z-scores. You guys probably remember that the z-score is the number of standard deviations a value is away from the mean. So a z-score of 2 is 2 standard deviations away from the mean. A z-score of -3 is 3 standard deviations away from the mean. Negative z-score is to the left of the mean, and a positive z-score is to the right of the mean. So, types of probability problems. When asked to find the probability of a normal distribution, it will be one of 3 conditions. So say the value we are looking for will be greater than z. So if the value you are looking for is greater than z, then we are looking for all values to the left of that number. Think back to our airport problem we did before. We are looking for a value of where it's, this is kind of more similar to an at most. So if we are looking for at most this value, and then you would look for the area under the curve to the left of that. I'm sorry about this pop-up that keeps coming up, guys. I asked IT for guidance, but I haven't been able to get a response for that. So again, if the number we are looking at is greater than z, we are looking for all values to the left. However, we can also be looking for our number which is less than z. So think back to our airport problem. These are the types of problems where you are asking what is at least this number, and then you are looking at everything to the right. You can also be looking for a range. So you're asked to find a probability of a normal distribution where you have a upper limit and a lower limit. Okay, we're going to go back to these slides once we look at the example. I'm just trying to create the framework and the foundation for these problems. We're also going to go back to this slide. I kind of want to do an example with you. So next we're going to find, how do we find the z-score? Well, there's three methods that we will use in this class to find the z-score from probability. So method one is using the table A2 from the textbook. It's actually pretty easy, so I'm okay with using this. Normally I go straight to technology, but I think this is easy enough. So table A2 is designed only for standard normal distributions. Remember, standard is where the mean is 0 and the standard deviation is 1. Table A2 is also has two pages with it. The leftmost page is for negative z-scores and the right page is for positive z-scores. Make sure you use the correct one since the numbers will be drastically different. So continuing that, things to note is each value in the body of the table is a cumulative area from the left up to a vertical boundary above a specific z-score. So say your z-score is, say z is -1. When you find the area under the curve, it would be everything to the left of that. So I'll say that again. When you're using table A2 and say you're looking for a z-score of -1, the value that the table will give you is the area of the curve starting from the z-score, so -1, and then everything to the left of that value. Positive z-scores, it's still everything to the left of the value, but see now how we are going past the mean. So again, I'll say that one more time. Say your z-score is 2.35. While you look at your table, you get your value. That value in the body of the chart gives you your area, or your area under the curve, your probability. And then you know that the probability that gives you is the total area under the curve starting from your z-score, a vertical line straight up, and everything to the left. It's cumulative. So how do you use the table? Well, the table, again, is broken down into a left is negative, right is positive z-scores. And you'll see, this is just a little snippet of it. There's the leftmost column will give you negative, say for example, a -3.4, and then this over here is the hundredths place. So you kind of add these numbers together. So say you want to know what -3.45 is. So you look at -3.4 plus that value, so that would be -3.4 plus 0.05, -3.45, and that corresponds to a probability of 0.0003. So let's just do a quick example. Make sure you understand how to use this table. What is the area under the graph, or the probability, remember, it's the same thing. Area under graph is probability for a z-score of -2.69. So we look at the left column, we find -2.6. Also look for 0.09. So that's -2.69 has a probability of 0.0036. You could also be asked, what is the z-score if the probability is 0.0040? Now you got to work backwards. So I'm looking through here. I'm looking for 0.0040 right here. That corresponds to -2.65. You can also find z-scores using your calculator. Here's some videos for that. And using StatCrunch as well, and some videos for that. So a bone mineral density, look at an example now. A bone mineral density test can be helpful in identifying the presence or likelihood of osteoporosis. The result of a bone density test is commonly measured as a z-score. The population of z-score is normally distributed with a mean of 0 and standard deviation of 1, so these test results seem to meet the requirement of a standard normal distribution. Again, that's our normal graph, mean of 0, standard deviation of 1. Okay, so we are asked, a randomly selected adult undergoes a bone density test. Find the probability that this person has a bone density score less than 1.27. So when we say less than 1.27, let's go back to that slide that we kind of breezed through earlier. So we are now looking at a value, this is type 1, of 1.37, and we want to know what's going to be less than that. So when you're looking at something that's less than a value, it's everything up to that value. So everything to the left of the vertical line drawn at the z value we are currently analyzing. So we can just straight look up our z-score from A2. We can use our calculator, or we can use StatCrunch. If we use our table, we know that 1.27 corresponds to 0.8980. I also encourage you to try this with your calculator and StatCrunch just to make sure that you are using them right. So the probability then is 89.8% or 0.8980. Okay, so now same problem, but now we want to know the probability that a randomly selected person has their result above -1. Okay, so now we're looking at type 2 of the types of problems that we're looking for. So remember, over here we were looking at where our value was less than or equal to. Now we are looking at, well, at least. So now we're looking at the values to the right of the vertical line drawn at the z-score that we are currently interested in. However, when we calculate z-score using the table, the z-score that we get is everything to the left of that value. So if we were looking at, I forget what number it was like z of -1. If we look at the table, that's going to give us everything to the left of that. Now we want everything to the right of that. So how do you solve that? Well, you just do 1 minus the value to the left, and that'll give you this value. So again, if we're using our tables, the value we get for the z-score that we're interested in will be everything to the left. It'll be the area leading up to it. If we want to know the area not under the graph that is shown in the table, it would again just be 1 minus that value. Okay, I'm jumping around a lot, so hopefully you follow. Okay. So again, if we use table A2, we should know that it is only going to give you the cumulative area from the left. But again, since we want values to the right, we have to do 1 minus the value to the left. And that's how we would get our table would give us a value of 0.1587, but we want the complementary value of that, so it would be 1 minus that value. Okay. Again, I encourage you to do these problems using technology just to make sure that you are seeing these in the different angles. And finally, the third type. So same problem, but now we want to know the probability of getting a density reading between two values. So between -1 and -2.5. We want to know the probability that a randomly selected person falls within those two readings. So sorry for keep going back and forth, but now we're looking at this slide. So now it's a range. So we have a number for the lower limit and the number from the higher limit. To find the area in between, you just have to subtract the two values from one another. Because if you think about it, if you get your z-score for this value up here, your upper limit, that would give you all this area under here. And then for your lower limit, it would give you this value over here. When you subtract the value from this from the value of that, what you are left with is just the values in between. And that's what we are looking for. So we find our our probability for a z-score of -1. We find our probability for a z-score of -2.5. We subtract the 2 out, and that's how we get our final answer. Some basic notation for you guys that we pretty much already went over, but this is just writing it out in a more organized form. And finally, finding the critical value. So find the value of z sub 0.025. So the notation of z sub 0.025 is used to represent the z-score with an area of 0.025 to its right. And then refer to the figure and note that the value of z would then correspond with a z-score of 1.96, since that has the area that we are interested in. So remember, so the z-score of 1.96 gives us an area of 0.025. That's what we're looking for. But one thing to note is that since this is symmetrical, a negative z-score of 1.96 would give us the same area as well. Kind of see how those two numbers are the same, how you're looking at the same way. So you just got to be careful to read the problem carefully to see what value they want. And that's just basically giving you the warning of, hey, you know, that 0.025 number comes up twice depending on if you're looking at greater than positive z or less than the negative z-score with that. And that's all for section 6.1. Thank you.